The figure shows the pin diagram of 8085. Let us discuss the significance of all the pin signals in detail. 8085 is a 40-pin IC with DIP package. It is dual inline package. The pin signals can be grouped as follows: power supply and clock signals, address bus, data bus, control and status signals, interrupts and externally initiated signals, and serial I/O ports. Pin number 40 is known as VCC, through which only we have to give you a plus 5 volts DC power supply. And pin number 20 is referred as VSS, it's a ground or a reference point. Pin number 1 and 2 is named as X1 and X2, through which only the MUP is driven with the clock signal. A crystal or RC network or LC network connections to set the frequency of internal clock generator. The frequency is normally internally divided by 2. If the operating frequency is 3 MHz, a 6 MHz crystal is to be connected between X1 and X2. The internal frequency of operation is available at the pin number 37, which is referred as clock out. So this clock out signal can be used as for giving input for the peripheral devices which are connected with the microprocessor. For example, in the case of timer 8253 or 8254, it requires a clock input. That clock input can be derived from the clock out of 8085, that is pin number 37. This is pictorially shown here. Between X1 and X2, a 6 MHz crystal is connected. So from pin number 37, the clock out, which will generate 3 MHz crystal oscillation frequency. 8085 microprocessor consists of 16 address lines. So 16 signal pins are assigned for address bus, which are divided into 2 parts. One is the higher order address bus, which is A8 to A15, which is unidirectional in nature. The second part is referred as AD0 to AD7, that is address data bus 0 to address data bus 7. So which is bidirectional and which can be used for a dual purpose. The AD0 to AD7 will act as a address bus as well as data bus. So which is normally referred as lower order address bus. Whenever an instruction is being executed, at early stage, AD0 to AD7 is used as address bus and alternatively as data bus for the next cycle. So the same bus AD0 to AD7, that is the address data bus 0 to address data bus 7, will act, one time it will act as a address bus, at another time the same bus will act as a data bus. So this is known as bus multiplexing. And the 8085 consists of 2 control signals. One is read bar, another one is write bar. Read bar is pin number 32, write bar is pin number 31. And it consists of 3 status signals, which is known as IO bar, M bar. S0 is pin number 29 and S1 is pin number 33. IO bar, M bar is pin number 34. Generally, whenever during the interfacing of peripherals and memory, this S0 and S1 is not being used. They use the 2 control signals, read bar, write bar, and one status signal called IO bar, M bar. And another important pin is ALE, that is address latch enable, which is pin number 30. So we know that lower order address bus is multiplexed with the data bus. So that ALE is used to demultiplex the address and data bus. How the demultiplexing is done is explained with the figure. Here you can see that from AD0 to AD7, whenever from AD0 to AD15, initially whenever an instruction is being executed, the address, that is 16-bit address, is loaded from AD0 to AD7. AD0 to A15, that is AD0 to AD7 and the A8 to A15. Then during the first T state itself, during the opcode fetch cycle, during the opcode fetch machine cycle, and during the first T state, that ALE, from the ALE of microprocessor, it will generate one pulse. So if the ALE is if a pulse is generated from ALE, it will enable the latch called 74LS373. The latch connections are given like this. That is, the input for the latch is from AD0 to AD7. So latch is nothing but it consists of 8 D flip-flops. So once if you give the enable signal through ALE, whatever may be the input which is given to the latch will come to the output as it is. So during the first machine cycle of the first T states of the first machine cycle, the address is placed in from AD0, lower order address is placed from AD0 to AD7. So that address is available after the latch. So this is how the address is demultiplexed. Now this bus AD0 to AD7 is free. So now this bus is used to connect the data bus. So the data bus from memory or data bus from peripherals are connected straight away through AD0 to AD7. This is how the demultiplexing is done with the help of ALE. And this table shows the status of the signals IO bar, M bar, S1 and S0 during the different operations performed by the microprocessor. During the opcode fetch, IO bar, M bar is 0 because either it is an opcode or it is a data, it is stored in memory. So it should be 0. Then if both S1 and S0 must be high. During memory read operation, IO bar, M bar is 0 and S1 is 1, S0 is 0. During the write operation, memory write operation, IO bar, M bar is 0, S1 is 0, S0 is 1. Similarly, you can see the other status signals during IO read, IO write, interrupt acknowledge, halt, hold, and during the reset of the processor. Then pin number 6 to pin number 10, or you can say pin number up to 11 is used for handling the interrupts. So interrupt is a signal sent by an external device to the processor to request the processor to perform a particular task or work. See, whenever we execute some program from the main memory location, the instructions are fetched sequentially and it is executed in a sequential way. So in the case of emergency, if you want to execute any routine, we can interrupt the processor. So if a microprocessor receives an interrupt, immediately the execution will be routed to the particular memory location which is allotted for the interrupt. After that interrupt service subroutine is completed, it will come back to the main program and it will do the routine job. Mainly in the microprocessor based system, the interrupts are used for data transfer between the peripheral and the microprocessor. The processor will check the interrupts always at the second T state of last machine cycle. If there is any interrupt, it accepts the interrupt and sends the INTA, that is interrupt acknowledge signal, to the peripheral. The vector address of particular interrupt is stored in program counter. As we know that always the executions start from the program counter, the processor executes an interrupt service routine addressed by the program counter. And it returns to the main program by RET instruction. So that ISR should be ended with the instruction called RET. There are two types of interrupts. One is called software interrupt, another one is hardware interrupt. Software interrupts are program instructions. It is just like a call instruction. These instructions are inserted at desired locations in a program. The 8085 has 8 software interrupts which are named as RST0 through RST7. The vector address for these interrupts can be calculated as follows. The interrupt number should be multiplied by 8. That will give you the vector address. Suppose if we take RST5, if you multiply 5 into 8, you will get 40. If you convert 40 into hexadecimal number, you will get 28H. So the vector address of RST5 is 0028. So for RST5, you have an opcode. Just if you execute the opcode for RST5, the execution location is routed to 0028. Similarly, we have RST0 to RST7. The table shows the vector addresses of all the software interrupts. Hardware interrupt. An external device initiates the hardware interrupt and placing an appropriate signal at the interrupt pin of the processor. Actually, if you look into pin number 6, it is called trap. Pin number 7 is RST restart 7.5. Then pin number 8 is restart RST 6.5. Pin number 9 is RST 5.5. Pin number 10 is known as INTR. These are all hardware interrupts. Actually, for every interrupt, one pin is allotted. So if the interrupt is, if any external device can generate a pulse and by using that pulse, it can interrupt the processor physically. If the interrupt is accepted, then the processor executes an interrupt service subroutine. The 8085 has 5 hardware interrupts. One is trap, RST 7.5, RST 6.5, RST 5.5 and INTR. The table shows the vector address of the interrupts. Here also, for calculating the vector address, if you take 7.5, you have to multiply 7.5 into 8. If you convert that value into hexadecimal number, you will get 003C. That is the vector address of RST 7.5. Then similarly, the vector address of 6.5 is 34, 5.5 is 2C, trap is 24. Among the 5 hardware interrupts, the trap is called as a non-maskable interrupt. It is unaffected by any mask or interrupt enabled signal, and it is also having the highest priority among all the interrupts. Then trap interrupt is edge and level triggered. This means that the trap must go high and remain high until it is acknowledged. In certain power failure, it executes a ISR and sends the data from main memory to backup memory. If there is any power failure, by using some external circuitry, immediately we can make an arrangement to give an interrupt at the pin number 6, that is called a trap. Once if the microprocessor receives a signal through trap, immediately the execution is routed to the memory location which is allotted for the trap. There you can write a ISR for moving the data from main memory to backup memory. Then RST 7.5, it is a maskable interrupt. It has the second highest priority. It is edge sensitive, that is, input goes to high and no need to maintain high state until it is recognized. It is a maskable interrupt. It can be disabled by using DI instruction, disable interrupt instruction, or system or processor reset, or after reorganization of the interrupt. It is enabled by instruction called EI instruction. Then RST 6.5 and 5.5. The RST 6.5 and RST 5.5 both are level triggered. That is, input goes to high and stay high until it is recognized. These are all maskable interrupts. It is disabled by using the instruction called DI or SIM, set interrupt mask instruction, or by system or processor reset, or after the reorganization of interrupt, which can be again enabled by EI instruction. The RST 6.5 has the third priority, whereas RST 5.5 has the fourth priority. So the priority goes like this: trap, 7.5, 6.5 and 5.5. The INTR is again a maskable interrupt, but it is not a vector interrupt. Unlike trap 7, if you take trap 7.5, 6.5 and 5.5, they have a specific location to execute the ISR. But for INTR, the location is not defined. It is disabled by, can be disabled by using DI or SIM instruction, or system or processor reset, or after reorganization of interrupt, which can be enabled by using the instruction called EI. Since it is a non-vector interrupt, if the microprocessor receives an interrupt signal through INTR pin, it will immediately generate a INTA bar, that is interrupt acknowledge signal from pin number 11. So by using this interrupt acknowledgement signal, by using some external circuitry, we have to place the address in the address bus so that the execution may start from that address. So by using some external circuitry, the vector address is to be given in the case of INTR, which is not internally given. So by using some external circuitry, the address to be executed is given by the program designer. The following sequence of events occur when INTR signal goes high. The 8085 checks the status of INTR signal during the execution of each instruction. If INTR signal is high, then 8085 complete its current instruction and sends active low interrupt acknowledge signal if the interrupt is enabled. In response to the acknowledged signal, external logic places an instruction opcode on the data bus. On receiving the instruction, the 8085 saves the address of the next instruction on stack and execute the received instruction. Then there are two instructions which are exclusively designed for controlling the interrupt as well as controlling the two pins of 8085 called SOD and SID, serial out data and serial in data. These instructions are called SIM, set interrupt mask, and RIM, read interrupt mask. The 8085 provide additional masking facility for RST 7.5, RST 6.5, RST 5.5 using SIM instruction. Similarly, the status of these interrupts, whether the interrupts are serviced or it is pending, for these kind of status can be read by executing RIM instruction. The masking or unmasking of RST 7.5, RST 6.5 and RST 5.5. This is the format of the 8-bit data which is shown below. See, the MSB is SOD, that is serial out data, that is a bit number D7. Bit number D6 is known as SDE, serial data enable. These two pins are exclusively designed for serial communication. That is, whenever this SDE bit is set into 1, if you execute SIM instruction, the content of D7, either it may be 0 or 1, that will be available at the 4th pin of the microprocessor. Right. So bit number D5 is don't care. Then you see bit number D3 is called mask set enable, which is used to mask the interrupts 7.5, 6.5 and 5.5. If MSB, that is bit number D3, if that the value of MSE, mask set enable flip-flop is set into 0, then the bits D2, D1 and D0 have no meaning, so don't care. But if MSE is set into 1, right, that means we are enabling the mask set enable flag. In that case, if the value of D2 is 1, that means which is the mask set flip-flop for RST 7.5. That means we are masking the interrupt 7.5. Suppose if the D3 value is 1 and the value of D1 and D0 is 1, 1. The meaning is we are enabling the masking facility and the interrupts RST 6.5 and RST 5.5 both are masked. If the value in D2 is 0, that means we are not masking RST 7.5. So the three interrupts, if you want, you can mask it. If you don't want, we can unmask it. The bit number D4, then additional masking facility is given for the interrupt called RST 7.5. One more extra facility. If you want, you can reset that interrupt by using this SIM instruction itself. Okay. See, suppose initially we may design to give 3 interrupts through RST 5.5, 6.5 and 7.5. Later on during the programming, we may not want to execute 2 interrupts 7.5 and 5.5 temporarily. So in that case, by using the SIM instruction, we can temporarily mask this RST 7.5 and 5.5. Again, the status of pending interrupts can be read from accumulator after executing RIM instruction. It's the read interrupt mask instruction. See, suppose in one particular application we may use 3 interrupts, 3 or 4 interrupts. Okay. Now you assume that initially we are giving interrupt through RST 5.5. Then before that interrupt service subroutine is performed, again another interrupt we are giving through RST 6.5. Now the priority for 6.5 is more than 5.5. So what will happen is the microprocessor will immediately, the execution will be routed to the particular memory location which is allotted for RST 6.5. In that case, that ISS for RST 5.5 is pending. So these kind of status, whether the ISS for one interrupt is completed or whether it is pending, so these kind of status can be known by executing the instruction called RIM. If you execute the RIM, the accumulator will be loaded with these contents, which is shown in the figure D0 to D7, and we can see what is the data, and based on that we can come to the conclusion. So it's the bit number D7, it's called serial input data. So here, suppose by externally you can set this pin value as 1 or 0. So if you can, by using one pulse generator, if you connect this SID, it's the 4th pin of microprocessor. You connect with the pulse generator, just you press the pulse, Whenever you're executing RIM, the status of the pulse is stored in D7, either it may be 0 or 1. Then interrupt pending I7.5, I6.5, I5.5 interrupt pending status of RST 7.5. The D5 is it will tell you the pending status of 6.5, and D4 is for 5.5. Now you see that bit number D3 is known as interrupt enable flag. 1 means interrupts are enabled, 0 means it is disabled. Okay, right? So how about the interrupt enable flag, whether it is enabled or disabled? So this RIM instruction is for knowing the status only. Right? By using SIM instruction, we are setting the interrupts, but by using RIM instruction, we can understand what is the status of the interrupt. So you see bit number D2, it is for mask 7.5. That is, if the value from bit number D2 is 1, that means that interrupt is masked. If the value from D1 is 1, that means we can understand that we have already masked that interrupt 6.5. Similarly, the D0 is used for 5.5. So SIM is for setting the interrupts as per our requirement. RIM is for reading the status of the interrupt. Whatever we set is correct, or what is the current status of the interrupt, where something is pending. So those kind of status can be read by using RIM instruction. Then reset signal. Following are the two kind of reset signals. One is called reset in, is an active low input signal. So once if the input which is given to this pin is active low, immediately the program counter will be cleared. So the execution will start from 0000. That is how the monitor routines are written, starting the address of the monitor routine is 000 zeros. So that is why they say the EEPROM address of 8085 must be 4 zeros. Because once if we press the reset key or reset in signal is low, the execution starts from 4 zeros. Okay. Then another pin is reset out. So once if the microprocessor enter into the reset state, it will generate an output signal from this pin to indicate that the MIPI is in reset condition. So this signal can be used to reset the other peripherals, external peripherals, which are connected with the microprocessor. Then another single bit serial I/O ports. I already explained about SID and SOD. These signals are used for serial communication. Either you can out data of 0 or 1 through SOD pin. Similarly, you can read the data 1 or 0 through SID pin. For these two applications, another signal which should be enabled is SDE, serial data enabled. That is the 6th bit, D6th bit. That should be enabled. That should be set into 1.